The cool thing about knowing the types of chemical reactions we can expect in chemistry is that now we can predict products. So with knowing nothing else other than the patterns that we see for certain types of chemical reactions, we can now say, if I have these kinds of reactants together, what kind of product should I make? And therein lies the power of chemistry, being able to predict the kind of chemicals we can make when we put two or more things together. By the end of this video, you should be able to predict the products just like any chemist would by utilizing the patterns you find in the types of chemical reactions we're already aware of. Time to let your knowledge on types of reactions take flight into this application of predicting products. Let's take a step back here and actually review the types of reactions that we have to work with so that we're not blindsided when we have to try and predict these products. The first kind of reaction is called a decomposition reaction. Just like when a body decomposes after it's passed away, it's decomposing into smaller parts. So I don't know if you've seen this cool thing now where they can take human remains and they actually turn it into soil. So you can become like a tree. You can become fertilizer for a garden if you wanted to. That's a form of decomposition, your body turning into soil and then using that to fertilize a tree or a plant or what have you. That's decomposing. So likewise, in a chemical reaction, you can have one reactant, like one human, that passes on and decomposes into multiple pieces. You'll break apart, right, as you decompose. So in a chemical reaction, you have one thing that breaks apart into multiple pieces. The example I gave in my previous video was nitrogen triiodide, which is the thing exploding above my head because it's breaking apart from nitrogen triiodide into nitrogen gas and iodine gas. That's the purple plume of smoke that you see is the iodine gas. We also have synthesis reactions. This is when you have two separate pieces or more. There could be 3, 4, 5 separate pieces, but they're all coming together to form one single product compound. So multiple pieces, one end product. We also have single replacement reactions. These are the ones I like to refer to as like the third wheel scenario. So like in the picture above my head, you can see that there is a couple together, but the guy is still going around the girl's back to try and kiss the other atom, so to speak. So you can kind of visualize this as well as there's a lonely atom, there's a pair of bonded atoms together to make a molecule, and this guy is going to boot out the Sharpie and bond now and have the Sharpie be by itself. So it's kind of a single replacement. One of the pens is replaced, one of the atoms is replaced, or one of the partners is replaced in a relationship to make a new compound. Then there's the scandalous reaction. Scandalous! The double replacement reaction. This is where both parties are switching their partners. So basically you go on a double date together to the bar and you leave with the other person's date. I also like to think of this as like that show, the real life wife swap. That's kind of the same idea that's going on here. So you're gonna end up with two compounds that switch their partners by the time they become products. So there was a double replacement of partners. We also have combustion reactions. When you think of combustion, you should hopefully think fire. Fire king. And one of the reactants, i.e. one of the things on the left-hand side of the arrow, is always going to be oxygen. And the other reactant is always going to be something that is made up of carbons and hydrogens. So some number molecule of carbons and hydrogens bonded together. And the products will always and forever always be CO2 and water for combustion reactions. There's not going to be any other products, just CO2 and water. And last but not least, we have neutralization reactions. This is where we have an acid and a base. When separate, both very caustic kinds of chemicals put together, and we create salt water. So Ba is a salt and ionic product where the cation and the anion from the acid and base hook up together, and then what's remaining is water that forms. So you essentially make salt water. So I've been using this term reactants and products quite frequently. We're predicting products today, i.e. we are predicting the stuff that will form on the right side of the reaction arrow. When I say reactants, I'm implying anything on the left side of the reaction arrow, and that's literally what that arrow is called. It's a reaction arrow. So all the things, all the parts, all the molecules that are on the left side of that arrow are called reactants. They're going to react together to form, that's the arrow, the products. And the products are always going to be on the right side of the reaction arrow, and that's all of the things on the right side of the arrow. So when we're predicting products or learning how to predict products today, we're learning how to predict all the things, all the molecules that show up on the right side of the arrow. But before we can predict what molecules form, we also need to be able to predict what state those molecules will be in. What do I mean by state? I'm not talking about the molecules hitchhiking over to Arizona or, taking a flight over to Washington. I'm talking about state as in solid or a liquid or a gas. And we need to know the state of the chemical too, because that's important. If our product is a gas and we're trying to capture it, we're not just going to create it in open space and let it fill up the room. That would be kind of pointless for us trying to create a product that's gas and then not being able to harness it. So we need to know what the state of our products are going to be as well when we're trying to form them in a chemical synthesis scenario. So when we write out our chemical equation, our predicted products with the reactants, we need to show whether the chemical is a solid, a liquid, or a gas by putting in parentheses directly after each chemical whether it is. If it says it's a solid in the question, we would write a little S after that chemical. So for example, magnesium solid reacts with hydrochloric acid. You would say, oh, MgS. It told me it was a solid. Likewise, if something's a liquid, you would put a little parentheses with an L or a little parentheses with a G for gas. Now there's one more state that we need to be privy to, and this state is called aqueous or aqueous. I've heard it said both ways. I say aqueous. And we represent that as parentheses AQ. Aqueous just means that it is in solution. So that means that it is dissolved in the solution. So you have basically an ionic compound, typically, it doesn't always have to be ionic because polar covalents also dissolve in solution, but it's something that is dissolved in solution. It's not a precipitate. It hasn't dropped out as a solid. It's in the solution. It's there, but you would have to separate it from the solution to get the product out if you needed to isolate it. So anytime you do come across an ionic substance in your products, you can pretty much bank on it being aqueous until we get to our solubility rules much later, where we'll learn about whether something can drop out as a precipitate. For now, just think about any time you have an ionic substance present that it's most likely going to be dissolved in the solution, and you can typically predict that its state is going to be aqueous. Anytime you see an ionic substance in your product side, it's most likely going to be aqueous. Most ionics are soluble in solution, dissolved in water, like potassium iodide or sodium chloride. So in this case, anytime you're doing this predicting product stuff and you need to put a state symbol after the chemical, please make sure that you're thinking, oh, that looks like an ionic, that looks like a cation and an anion, or that looks like a metal and a nonmetal bonded together. So it's got to be ionic. It's likely going to be aqueous as my state symbol. So let's just try this chemical equation with just the state symbols, just to kind of get the idea before we jump into predicting products and hurt our brain with trying to predict the future, essentially. If we read this chemical equation in words, it says sodium metal reacts with a solution of hydrochloric acid to form or to make an aqueous sodium chloride and hydrogen gas. I've written that out for you here. So sodium, that's our Na, metal. Metal is a solid. It's typically a solid. There's only a few that would be a liquid at room temperature. So we can pretty much guesstimate or predict that it's going to be an S here after the sodium metal, the Na. Then we have a solution of hydrochloric acid, that's HCl here. And now I'm telling you it's a solution. A solution would imply that aqueous that I was telling you about before. A solution is different than a liquid. A liquid is something pure. When we're talking about a solution, it's something dissolved in something else. So in this case, hydrochloric acid is probably diluted with some water, and that's what would make it a solution. It would make it aqueous. So we need to put a Q in the parentheses after HCl. To form or to make aqueous sodium chloride. So sodium chloride is NaCl. Again, aqueous is implying that NaCl, salt, is dissolved in something, likely whatever leftover water was from the solution in HCl. So we're going to say AQ after the NaCl. In other words, if you were to have this reaction going on in a beaker, you wouldn't see just table salt magically appear out of the solution. It would be there, you would have created table salt, but just like if you add salt to water, you don't just see it floating around in the glass necessarily. You'd have to boil away the water to get to the salt. And finally, we have hydrogen gas. H2, that's a diatomic. There's two of them. We never just have an H alone. And I tell you it's a gas, so we would put a G after it for gas as our state symbol. So you might be asking yourself, well, when am I going to use L for liquid then as my state symbol? Typically, if you have something reacting with water, H2O, or say acetone, if it's pure acetone, those would be examples of where you would use a pure L for liquid. So now that we've had that refresher on the different types of reactions and also the state symbols that can go with them, let's predict the products of these two chemical equations above my head. We have NaOH and HCl. Hopefully you're gathering that this is a reaction between an acid and a base, according to the patterns that we saw for our types of chemical reactions. Well, how did I get to that point? Well, if we're thinking about in terms of decomposition, that would have had to have been one chemical, one molecule breaking up into many pieces. Here we already have two molecules on the reactant side, so it can't be decomposition. How about synthesis? Synthesis would be implying there would only be an H, for example, and there would only be an OH on the other side, and those two would come together to form H2O. That's not what we're seeing here. Both of these molecules have more than one atom type present, so it can't be synthesis. What about single replacement? Single replacement would have to imply that one of these molecules would be by itself. So for example, NaOH and H just by itself. That could be maybe a single replacement because you have one alone acting as a third wheel that's going to kick out one of the happy couple members. So it's not going to be that. Now you might have thought, okay, well this does sort of look like a double replacement, and you're right. A double replacement is a generic reaction type. Neutralization is between an acid and a base. Now remember, neutralization is a type of double replacement reaction. So in a way, we are doing double replacement, but more specifically in this reaction, we're doing neutralization because it happens to be between an acid and a base. So what would this look like then? We know that neutralization reactions will always end up with an ionic salt and water. One of our products has to be water, H2O, and the other one has to be an ionic salt. Well, how do I know which ionic salt it is? I got the H2O from this H hooking up with this OH, H2O. So the only thing that's left over now is Na and Cl. Those must be our cation and anions that are going to pair up together. So let's try putting Na and Cl next to each other and check those charges to make sure they balance. That's muy importante for this kind of stuff. You have to make sure that those charges balance. Otherwise, when you try and balance the entire chemical equation in a later lesson, this would totally throw off your game. So always still make sure you are putting the charges in the upper right-hand corner to check and make sure that those charges actually do cancel to zero. And if they don't, make sure you drop and swap. In this case, 1 minus 1 does give me 0, so I can just keep NaCl together, and those would be our products. Look at us predicting the future of what chemicals would form. For the next example, I've already told you it's a combustion reaction. We know it had to have been combustion because we have something made of carbons and hydrogens reacting with oxygen. And if it's combustion, where we have that scenario, the only two products that will always form for combustion are CO2 and water. How easy and straightforward it can be to predict the products if you know the patterns of the types of reactions that we have. So try writing out this chemical equation before I tell you what it is. Go ahead and pause the video here and give it a try.
2 hours later.
Sodium metal, that's a solid, reacts with, that's a plus sign, a solution of hydrochloric acid, HCl aqueous, to form or make, that's our reaction arrow, sodium chloride, NaCl, and hydrogen gas. Oh no, I didn't tell you sodium chloride solution or sodium chloride gas or sodium chloride liquid. I didn't tell you the state. Whatever should we do? Remember that sodium chloride is Na plus 1, that's a metal. Chlorine minus 1, that's a nonmetal. We should know that that's an ionically bonded chemical compound. And because it's ionically bonded, we can assume that it's going to be aqueous when we predict the products. So in this case, we would assume it would be AQ. Now when we look at this overall reaction, what type of reaction is that? Hopefully you see that I have one lonely third wheel and I have a date going on over here between HCl. Na comes in and kicks out H. So Na, the third wheel, is claiming Cl as its date now in NaCl on the product side and leaving hydrogen gas, H, all alone in the cold, but not really because H just found itself. It's a diatomic, so it's still not alone. What type of reaction is that? There's one single atom that replaces another in the compound. So we would call that a single replacement reaction. But what if I only gave you the Na solid reacting with HCl aqueous? Would you be able to recognize that there's a third wheel here and that there is a date going on here? Hopefully you'd recognize that pattern. And the battle plan you would need to know before being able to even predict the products that would form is first and foremost figuring out the type of reaction it is. So when we look at the reactants, we need to compare it to all of the different types of reactions we have at our disposal and see which one fits the bill the best. So step one to predicting products is first identify the reaction type you're even working with. Use the pattern of what was given for the various types of chemical equations that we have, using those general formulas as comparisons. Step two, predict the products based on the reaction type. So just like we know for combustion, it would always make H2O and water, then you can predict that those would be the products if you happen to have the reactants that match a combustion reaction. Make sure you identify the elements that would be separated apart or put together, and keep in mind that some will always have the same products, and if you're forming ionics, you need to make sure the charge is balanced through drop and swap. Step three is then to actually balance the charges for ionic compounds through drop and swap. And also remembering that your diatomics will never be alone. So that's the H, the O, the N, the Cl, the I, the F. All those guys are never going to be by themselves. They're always going to be H2 if they're not bonded to something else, or O2, Cl2, F2, so on and so forth. And step four would be to add any predicted state symbols based on what you know about the state symbols and what the equation was giving you if it was written out. Solid, S, liquid, L, G, gas, AQ, aqueous. So let's give this one a go. Can we predict the products for these two reactants? These two reactants are going to come together and make some form of product. Let's first see what we have at our disposal. We have Na bonded to carbonate, CO3, that's a polyatomic ion. And we have barium, Ba, with nitrate, also a polyatomic ion. So in this case, we have a double date going on. The only type of chemical reaction that fits the double date standard or scenario is going to be that real life wife swap scenario or double replacement. So in this case, both partners are going to switch. How do I know which one to switch with what? That's a great question. We're not going to pair cation with cation, and we're not going to pair anion with anion. That doesn't make any sense. We can't shove two negatively charged atoms together, and we can't shove two positively charged atoms together. So we would not, no, under no circumstances ever, would we put Na with barium. Big no-no. Don't do it. That's trying to put two cations together. No. We would not put our carbonate and our nitrate together. Big no-no. We can't put our two negatively charged things together. So what we have to say is, oh, okay, if this is double replacement, then we're going to put our Na with the anion of the second molecule. And we're going to put our Ba, our barium, with the anion of the first molecule. That's going to be our pair up or our double swap, our double replacement. So now what we end up with is barium and CO3 minus 2. Now, what's the charge on barium? Check your periodic table, and you should see that barium has a charge of plus 2. That's convenient. 2 minus 2 gives us 0, so those charges balance. And then we have also Na is now going to pair up with NO3. That's our nitrate, NO3. Now, nitrate from the polyatomic ions list has a minus 1 charge, and sodium from your periodic table has a plus 1 charge. Convenient in that 1 minus 1 gives us 0, so we don't even have to do drop and swap here. We have predicted the products to be barium carbonate and sodium nitrate. Okay, that's cool and all, but now we need to also predict what state these are going to be in. These both happen to be ionic compounds, so we would predict that both of these would be aqueous, AQ as a general rule until we figure out what the solubility rules are in the future. For now, whenever we see ionics, we're going to predict that it's aqueous. Think you got it? Go ahead and pause the video here and give these guys a try.
2 hours later.
All right, so for the first one, we have methane gas, CH4, burns. Well, okay, so we have something that's composed of carbons and hydrogens, and we're saying it burns. Hopefully the first thing that comes to your mind is combustion, fire. So we've got CH4 plus oxygen for the burning aspect of it. And we know that combustion reactions will always, and forever form CO2 and water. How about the state symbols on that? CH4 is a gas. I tell you it's a gas, so we're gonna put a little G after it in parentheses. We're gonna put a parenthesis after the O2 and gas. CO2, also a gas, the thing that you breathe out every time you breathe, and provides plants with some necessary carbons. And last but not least, we have water, H2O. You might be tempted to write an L after that because it's water, right? Obviously. But water doesn't just exist in a liquid state, remember? And we're talking about burning here. We're talking about fire, combustion. So the likelihood of water just like pouring out of your campfire, if you want to think of it that way, is slim to none. I mean, if that's happened to you, by all means, please tell me about that in a story in the comments below because I want to hear it. But as far as I understand, whenever there's a fire, there's not just liquid water that pours out of it. So in this case, we're going to say, the water here is probably in a vapor form, so it's probably a G for gas. How about the next one? We have aluminium, which is a metal. We're going to predict right off the bat that that's a solid. And we have silver nitrate, AgNO3. Silver nitrate is an ionic compound, so we're going to predict that it is aqueous, AQ. We have a lonely atom, Al, and we have paired up molecule. So the only pattern this fits for our types of chemical reactions is a single replacement. And since we know that it has to be a single replacement by the pattern, we know that aluminum, which is a positively charged ion, would have to take the place of the current positively charged ion, silver. It would look something like this. Al plus 3, that's the charge it forms from the periodic table, next to NO3 and nitrate from our polyatomic ions list makes a -1 charge, plus silver, Ag, now all by itself. Anytime we have these charges next to each other, we have to do our drop and swap. So I'm going to take that 3, put it down there, take the 1, put it down there. And what I end up with is Al, NO3, 3. Now the last thing we have to do is add in those state symbols. Now the silver is a metal, so if you predicted maybe that it's a solid, maybe it drops out of the solution as a precipitate, okay. But we're also maybe going to predict that it could still be in solution. It could be aqueous. Remember, this is just predicting. We're getting a good idea. And likewise for the second one, AlNO3, 3, is an ionic compound in solution most likely. So don't get too caught up on the state symbol predictions, but predicting these is the more important thing. How about let's try it number 3. We have Na sodium plus Cl2, chlorine. In this case, we have 2 singular types of atoms, and the only bill that fits for our types of chemical reactions is 2 separate types of atoms coming together to make 1. So here we would take Na plus 1. Don't forget those charges, we gotta make sure they're balanced. And Cl minus 1. We're just going to take the atom type, not the number of them. We don't care how many there are at this point. And make sure that those charges balance. 1 minus 1 gives me 0. Awesome. So those two are going to come together and just give us NaCl, or table salt. Your prediction of the state symbol here is as good as anyone's guess, except it's probably not going to be a gas and it's probably not going to be a liquid. So if you said solid or if you said aqueous, you're probably right for either, depending on the scenario. Let's just put solid or aqueous. How about the reactant side? Sodium is likely a metal in solid state, so we would write an S. And chlorine is usually existing as a gas. Remember, it's a diatomic, it's a halogen. So most of those are existing as a gas, especially at room temperature. So we would say G for chlorine. And our last reaction for predicting products is Na2CO3. So there's 2 different groups there. And CaCl2, two different groups there. This is definitely a scenario of double replacement, real life wife swap. Remember, we're going to take our cation and pair it with the anion of the other molecule and vice versa. So we're going to take the sodium and pair it with the chlorine and take the calcium and pair it with the carbonate. So what we get is Na plus 1 from the periodic table, Cl minus 1 also from the periodic table. Notice I didn't take the 2 over. I don't care how many there are. I'm just taking the atom type and then figuring out how many there are. 1 minus 1 gives me 0, so that's just NaCl. Plus, calcium is our cation for the second molecule, and calcium forms a +2 charge. And we're going to pair it now with carbonate, CO3, which is a polyatomic ion with a -2 charge. Conveniently, those two cancel out, so we don't even have to do drop and swap. And we're done with predicting the products there. What about the states? Anytime we have a double replacement reaction, the likelihood of it being all aqueous is pretty high. So we're just going to say, okay, these are probably all in solution. They're all ionics, so we can assume that it's all going to end up being aqueous as well, until we learn our solubility rules later on, when we can determine if something will truly remain in solution or if it will crash out as a precipitate or as a solid. For now, don't worry about that. We're just going to say anytime there's ionics, we're pretending that they're all going to be aqueous. These here are a little bit more challenging because I've written them out. So not only are you going to have to figure out what the products are and the state symbols, but you're also going to have to make sure that you write out the reactants correctly from the words. So make sure you've got your periodic table handy right next to you, and you can use that to help you write out the symbols first, then figure out the type of reaction based off the reactants, predict the products based off of that, and include your state symbols, or your predictions of state symbols, that is. And now that I'm pretty sure your poor brain feels like my little brain hand puppet friend here, and your eyeballs are probably doing just that as well, even the thought of predicting products, you're like, oh my gosh, help. I'm wishing you the best of luck in predicting your products, minus any kind of headache that they may cause. Till next time, see you later. Have a ducky day.
No ducks, no glory.